So, welcome to this topic on NVIDIA GPU memory organization. So, NVIDIA has organized there are different types of memory in their architecture, and the main aim of this memory organization is to speed up the memory access and the performance of the memory for scientific and AI workloads. So, let us discuss how many different types of memories are available in NVIDIA GPUs and what are their uses. So, you can see here that in NVIDIA GPUs there are several memory spaces are available. You can see that the first one is a global memory. So, global memory is a space, you can say that it is a space, you can say it is a space available or a space provided by the global RAM. It may be RAM, may be GDDR RAM or HBM RAM. And this memory is accessible by all the threads and its capacity is larger, is high capacity, but it has a high latency as well, and it is used to store the data that need to be shared across multiple blocks. Second memory is the shared memory. This memory is accessible by all the threads, but within a particular block. It has a low latency, and you can say it is similar to cache, but earlier days the shared memory and cache memory was separate, but these days the shared memory we are defining in a L1 cache itself. So, we can say that both are similar, but purpose may be different. It is used for the data sharing and the communication within a block. Next is a local memory. Local memory is a private memory or private space for each thread to keep their data, and it is used for the register spilling and automatic variables that do not fit in the registers. Suppose one thread has to use around 8 registers, but in case it has a more data, but 8 registers are not able to fit the data its value and spilling over. In that scenario, this local memory come into the action automatically, and the spillover section will be allocated to the global memory. So, that is the reason is that local memory is always private to each thread. Next is a constant memory. It is a read only memory and it is accessible by all the threads. It is very useful whenever we declare any variable with some constant. So, that kind of values, so constant values which is required by all the threads will be declared in the constant memory. It is a low latency and it is optimized for the broadcast to all the threads. Next one is a texture memory. It is a read only memory and it is optimized for the spatial locality. So, you can say that this kind of texture memory is useful for the image processing or graphic processing. Next space which is used to store the variable store the data is a register, is the fastest memory space, private to each thread, but it is limited in size. So, each memory has their own advantages and their own disadvantages. Now, let us see the order of the memory. They are organized in the NVIDIA GPU in terms of speed and the capacity. If you see this particular direction line, if you see here, the capacity of data storage capacity of global memory is very high compared to the register. So, you can say that the capacity, storage capacity is decreasing as we are moving to the upward direction, means we are moving from the global memory to the register, the storage capacity is reducing. Similarly, if we see this particular direction, the accessing speed is getting slower. So, accessing speed of register is fastest. As we are moving to the global memory, the accessing speed is reducing, means latency is high. Apart from this memory, there are some caches is also available on each NVIDIA GPUs. So, we have already discussed about the L0 cache, L0 instruction cache and data cache, which is available inside the each process block. Apart from that, there is a L1 cache and L2 cache. So, you can see that the L1 cache is a on chip, a fastest access storage, which is accessible by single thread. So, L1 serve as the overflow region when amount of active data exceeds what the SM register cannot hold. Or you can say, in other words, you can say that frequently accessible data, frequently used data is to be kept in the L1 cache. Similarly, the L2 cache functionality is there. It is retaining the copies of data that travel back and forth between the SM and main memory, and it is shared by all the SMs. Now, shared memory, it is a physical memory, resides in the same memory as with the L1 cache, which I already discussed with you earlier. Architectures, NVIDIA architectures, shared memory was separate and L1 cache was separate, but nowadays the shared memory is dynamically being declared in a program, and it is resides on the L1 cache. But in terms of functionality, it differs from the L1, that all its data may be accessed by any thread in a thread block, and the application can set dividing the lines between the L1 and shared memory. Next is a global memory. It is a main memory of the any GPU device. And earlier we were using the GDDR RAM as a global memory, and these days we are using HBM memory, high bandwidth memory, as a global memory. Local memory. Local memory is a part of global memory, means it resides in the global memory, and it is mainly used for the variable that cannot fit in the limited registers assigned per thread. And each thread has its own private local memory, and it is constrained by the total global memory available on the chip, on the GPU. That means, how much of the space available in the GPU, that much of memory can be used for this purpose. Then is a texture memory. The texture memory is technically the part of GPU's global memory, However, they are managed differently from the standard global memory to improve the performance. It is a read only memory and it is optimized for the spatial locality, and it is accessed through a specialized texture cache. So, simple terms, even though it is out of scope for this course, but you can say that whenever you are dealing with any image processing or video processing kind of application. So, then application developer must use this memory a lot. Next one is a constant memory. Constant memory is also the technically the part of the GPU's global memory, and it is also managed differently from the standard global memory. It is also a read only memory, but to optimized for the cases where all the threads need to access the same data simultaneously, means all the threads which has been launched in a particular application want to access the same data simultaneously. In that scenario, this constant memory is very useful. The size is limited, it is up to 64 kilobyte of size. Similarly, if in a shared memory also there is a 48 kilobyte of space can be allocated in L1 cache, but if you see the different architecture, there may be some variations in a constant memory as well in shared memory size. So, it is always recommended to refer the data sheets. Now, the relationship between shared memory and L1 cache. So, as I already discussed that the shared memory can be configured on the L1 cache space, and what are the remaining space after declaration of the shared memory on L1, whatever the space will be left, it will be used as a L1 cache. So, thing is that the shared memory is being controlled by the programmer and it is going to use for the communication and data sharing among the threads within the same block. So, important thing is that it is being controlled by the programmer. Suppose is a maximum limit is 48 kilobyte, and if you want only 4 kilobyte you can allocate. If you want 16 kilobyte, so you can programmer can allocate that much of shared memory space on the L1. If you see, the L1 cache is used for the frequently accessed data to reduce the latency from the global memory. It is well known, but important thing is that this action is not controlled by the programmer, but it is but this action is controlled by the hardware itself, and the size of L1 cache can vary depending on the micro architecture or architecture implemented in the particular GPU. Here I am just representing the CUDA memory API functionalities. So, where this malloc function is used and where this CUDA malloc function should be used, and where this free function is used and where this CUDA free function. So, free function CUDA malloc function and free function is used on the system memory space, CUDA malloc and CUDA free is used for the GPU memory space. Now, let us discuss the memory management functions. So, there are few more management functions, but here I am using explaining the three widely used memory management function. The first one is a CUDA malloc. So, CUDA malloc basically allocates the memory on the device. Whenever I am talking about the device, that is a GPU, and this red color content is representing how this function has been declared. So, you can see that d underscore a is a variable and how much of the size must be allocated for this variable. So, it is telling me that n into the size of, it may be int, it may be float, any etcetera, whatever. So, each int register, if you want to store the int value, and any int variable needs 4 byte of space to represent one element, and it has on n elements. Suppose if my value of n, if my value of n is 10, then how much of the space I should reserve? So, 10 into 4, almost 40 byte of space should be reserved or allocated for this variable. If n is changing, the size of the space to be allocated for the variable to be increased or decreased, vice versa. Next function is a CUDA free function. So, CUDA free function is just telling you that whatever the space has been allocated and reserved for this particular variable, you can see the variable is also provided to CUDA free. So, whatever the space is reserved for this variable, it should be freed, or it should be released for the other function. Next one is a CUDA mem copy. So, basically it copy the data from the host to device. So, here you can see it is indicating the destination and it is indicating the source and how much of the count, how much of the size should be reserved, and this portion which I have explained here is indicating the direction of the data movement, that is kind. So, if you see that if I am using this, passing this attribute host to device, then data will be moved from host to device, means system memory to the GPU memory. When I am using this, my data will move from the device, means GPU memory, to the host memory. Host memory means system CPU's memory. If I use CUDA mem device to device, if I pass this attribute, then the data will copy from one device to the another device. Here you can see the same detailing I have detailed or explained in a more detailed manner. So, used to allocate the memory on the GPU, and parameter is we are going to pass is the pointer and the size. Similarly, if you want to free, so we are providing the device pointer, so which location of the memory to be released. In mem copy, in mem CUDA mem copy function. So, I am just providing more detailing about the action which is happening because of this attributes which we are going to pass in this function in a place of direction. Now, there are a few additional functions I am going to discuss here. CUDA mem copy async, this is the additional or advanced function, memory management function you can say. It performs the copy asynchronously, basically in background. It will keep on performing the data copy operation, and this allows the CPU to continue executing the operation while data is being copied in background. So, this kind of function can give you the improved performance in certain scenarios. So, what are the parameters you have to pass with that? you have to provide the destination, you have to provide the source, count means size of the data in terms of byte, then kind means direction you have to provide, and then stream, on which stream you want to apply this. If you use pass the 0, so that means it is a default stream, you have to apply this function. Now, CUDA mem copy to symbol. This function is used to copy the data from the host to a device symbol. So, whenever the word device symbol comes, so you can think it of like the variable with any variable which is declared with the device qualifier and the constant qualifier. Data will be copied to this variable which is declared by the device and constant. So, we call it as a symbol. NVIDIA, they are calling it as a symbol. So, what are the parameter we are going to pass here? So, first is a symbol, source and count. Similarly, there is another function, we call it CUDA mem copy from symbol. It was a to symbol and this is a from symbol, means a variable is declared with a device and constant. So, what are the data that particular variable has, that is to be copied from that symbol to the host. It is just a reverse operation of the previous one. Now, I will explain you about the CUDA programs. So far we have understood the architecture, we have understood the workflow, we have understood the various data types, various functions available in CUDA programming model, various variables which we can declare with some qualifiers supported by the CUDA programming model, various vector types, as well as we have understood the different types of memory that are available in NVIDIA GPUs and their uses as well. So, now it is a time to see how to write the program that will be executed by the GPUs. So, here you can see the first hello world program and you can see this is a very simple function and the name of my function is CUDA underscore hello. Void is a keyword, you know that it is a standard C++ keyword. To make this function as a CUDA function or CUDA kernel, we have to write this qualifier global. If I am not defining this global keyword here or global qualifier here, then this function will be a simple CPU function. Now, I have to write another program in the main program and in this main program we have to call this GPU function which we call it kernel. So, you can see that int main, you know that int main is a standard C function and within this function we are calling basically CUDA underscore hello kernel and this triple angular brackets is the syntax to launch the kernel on the GPU and this brackets we have to pass the input, because in my function I have not used passed any inputs here. So, it is blank. So, I am using the blank here, and this 1 and 1 is basically it is indicating the number of blocks, and it is indicating the number of threads per block to be launched on the GPU. So, basically that, as we have discussed about the global qualifier, that time I had discussed that whenever this keyword comes, so this keyword can be called from the CPU, but it must be execute on the GPU. So, this program is going to execute int main program or int main function is going to execute on the CPU, and when CPU come across this, so it indicates that this is a kernel function and this should be execute on the GPU. So, basically CPU is calling this function, but it will execute on the GPU. Now, just see the comparison of two hello world program here is a normal C hello world program. This is a GPU hello world program or normal C, or you can say it CPU program. So, keyword we are using void here, and here also I am using void, and here also I am using void in both, but only difference is this qualifier I am passing to make this function as a CUDA function. Now, again this is a function. When I want to use this function in a main program, so I have to call this function in a main program, you can see here in a C program, and here is also again I am calling the CUDA function in a main program, but only thing is that the additional thing I have to pass is we have to tell that how many blocks and how many threads should be used to launch this CUDA kernel. This is only the difference. So, this triple angular brackets is known as the execution configuration of GPU, is a syntax for it. Now, this is a next level of hello world program. So, you can see that this program is same here. This is printing the hello world, but what I want that which thread is printing this hello and which block it belongs to, right. So, which thread is printing the hello world and this thread belongs to which block, both information I want to print. So, now is a kernel function, you know that, I think you have a got sufficient idea about how to write the kernel function that will execute on the GPU and how this kernel function should be launched by using the kernel configuration. These two things you have understood now. So, now I am just launching this hello kernel in this program. So, I am again passing these two parameters, you can see here, number of blocks and blocks underscore width. So, number of blocks is telling I have defined here number of blocks means this hello world program should be launched in a 2 blocks and each block must have 16. So, that means it is passing here 2 and it is passing here 16. In previous case, if you see, I am directly passing some number 1 or 2, and if you want you can change these numbers and you can execute this program and check the output. Similarly, here also you can change the number of blocks and blocks underscore width number, and learner wants to know more, they can execute this program. So, it is telling me that there will be a 2 blocks, this hello kernel will launch in a 2 blocks, and each block has a 16 thread T0 to T15, T0 to T15. So, that means this block in x direction has a 0 number and this block has in x direction as a 1 number. So, it will print like that, hello world, I am thread. It will print first of all, suppose is a thread ID 0 in x direction, thread ID is 0 here, from sorry, we have written in block, block will be 0. In case if this thread is printing, then it will print like this in block 1. You can see thread ID is same for both the blocks, because we have, I am not calculating the global or unique thread index. I am using the same thread index which is present inside the each block. So, thread 0 is present in block 0, thread 0 is present in block 1 as well.